Okay, so welcome back. Let's start the second half of the day. And in this half, we're going to have 3 talks, 1 hour each. After 2 talks, we're going to have a coffee break. So the second session will be started by Peter Scholl, who is a newly anointed assistant professor at Aarhus University, Denmark. Of course, I know Peter from many years, so we have shared a couple of common working places. When he was a postdoctorate, I was a postdoctorate with Nigel Smart. He was doing a doctorate, and he was very young and enthusiastic, always ready to soak in the new knowledge coming out of MPC. And today you can see that he has a very, very impressive resume with many good papers. And he's going to talk on multi-party computation in the pre-processing model. And this is actually the complementary setting. He's going to consider dishonest majority. So the first talk, which was given by Professor CPR, that was in the honest majority setting, right? If you recall, t less than n by 2. And he's going to start with the dishonest majority setting. He's going to start with the benign model, passive and semi-honest, and from there he will take on and build. So with that, I would like to welcome him on the stage, and over to you, Peter.
Thanks very much for the introduction, and thank you all for being here. It's really a pleasure. So yeah, this will be another tutorial, this time a little shorter, a little less in depth compared with the honest majority one in the morning. So I'll try and kind of give you a flavor of the basics in this setting of dishonest majority in the preprocessing model. So as you saw earlier, when you have an honest majority of parties doing MPC, then you can actually do MPC unconditionally without any security assumptions. And that's very nice, but when you move to beyond half of the parties being corrupted, this is no longer possible, and you can't compute even very simple functions without adding some extra computational assumptions. So in this setting, I'm going to consider the strongest kind of dishonest majority, where any number up to all but one of the parties might be corrupted. And we'll be looking at computing general functions, so we need computational assumptions. And this also means that we can't get the full security notion that you could get in the honest majority setting, which you need to settle for what we call security with abort and unfairness. So this means that the adversary can decide to kind of stop participating or cheat in such a way that the honest parties won't learn the output of the function, maybe even in an unfair way where the adversary might learn the output first and then deny it to the other parties. And again, if you have an active adversary, these kind of things are unavoidable in the dishonest majority setting. So this is kind of a little bit maybe depressing compared with the honest majority setting. But there's one kind of nice saving grace, which is if we use what we call the preprocessing model, then we can actually do much better and get away with unconditional security and no longer these computational assumptions. And that's what I'm going to focus on today. But note that even in the preprocessing model, we still need security with abort. Okay, and as before, the adversary will be static corruptions, although most of the things I talk about, I think, also apply to adaptive adversaries, but let's not go there for today. Okay, so the outline is going to be starting off with some passively secure protocols. First off, this very simple protocol called one-time truth tables, which is possibly one of the simplest protocols you can see for general two-party computation. It has some efficiency disadvantages, which you'll see, but it's a very nice kind of example to get you started. And then we'll look at something maybe more expressive and efficient, which is general MPC for arithmetic circuits, essentially a passive variant of the classic GMW protocol. And then in the final part of the talk, we'll look at getting active security, for which the main tool we use is information theoretic MACs, where I'll talk about 2 different kinds of MACs you can use to create active security, which are these pairwise MACs used in the BDOS and TinyOT protocols, if you've heard about these. And then this more efficient representation called speed-style MACs, which is a kind of global MAC instead of the pairwise ones. Okay, so as usual, we have multi-party computation, a bunch of parties who want to compute some function. And then the security guarantee of this is, of course, that this would emulate this ideal world process, which is where the parties give their input to the trusted third party, who delivers them the output. Now, in the preprocessing model, we consider not having a trusted third party, but having some kind of third party who will generate some preprocessing data in advance of the computation being done. So it's still trusted, but it's not trusted to see the inputs of the parties. Okay, so in this case, this preprocessing will be some magic box which samples some random data, say R1 up to Rn, and then delivers this to the parties. So each of the parties will get some portion of this random data. And then the idea is that the parties will then use this data in their online phase when the inputs become available, and they can hopefully use this to do the computation more efficiently or easier than they would have been able to do without having the preprocessing phase. So the main advantage is that this online phase can actually be very lightweight and, as I said before, entirely information theoretic, such that in many cases the computational work of the parties is actually only a small constant time slower than the computational cost of doing the plaintext computation on clear data. So this is a kind of very nice model. I hope that motivates it well. Although you might be wondering, okay, how does this preprocessing actually happen? Like if you want to implement this in practice, where does it come from? So today I'm not going to go into so much detail on that, and just imagine we have a trusted dealer who will generate this data as we request it. But in practice, there are a few different things you can consider, like probably most commonly is to use another protocol where the parties interact to generate this data in a secure way. Of course, then this protocol inherently needs computational assumptions like oblivious transfer or homomorphic encryption. And there'll be more on some techniques for doing this in my other talk on Wednesday or maybe Tuesday now. But alternatively, if you don't want to run a more complicated protocol, you could consider a third party who is generating this, and as long as this third party doesn't collude with any of the other parties, then the protocol is secure. And there are even things you can do to protect against a malicious malicious dealer who may kind of try to generate the randomness in the wrong way. You can kind of check that they do this and protect against that. And then finally, another option is to use some kind of trusted hardware device, which would typically have a cryptographic key embedded inside it, which is used to generate the random data and given to each of the parties. So you might say, if you're going to use trusted hardware, then why don't you just kind of use SGX and do the whole computation on that? But actually, I think using this just for preprocessing is a much weaker requirement on the security of the hardware. So the only thing you have to protect is this kind of secret key used to generate the randomness. You're not protecting an entire computation, which could be something much more complicated as you would if you're putting it into SGX. So there's a few reasonable ways of doing this, and I think the kind of nice thing about this model is that you get very simple computational operations in the online phase. It's something that you can easily go ahead and implement, and even if you don't want to do the more expensive offline phase, these other alternatives, I think, provide reasonable compromises that could be useful in practice. No, I'm saying that you can go for the trusted hardware, yes. Yeah. Yeah, but you could generate it in a kind of streaming manner, so on demand. As long as the hardware can have some state, then that should be possible. Okay, so the first topic is the one-time truth table. So this is this kind of very simple two-party computation protocol for any function, with the downside that it's actually very inefficient. Just a quick note that this can actually also be extended to multi-parties, more than two, and also active security, using some of the techniques I'll talk about later without too much difficulty. Okay, so it's called truth table protocol. So the kind of clue is that the first step is you take the function you want to evaluate, and then you look at the truth table representation of this function. So here's a simple example of a function with two inputs. Say if x is on the left and y is on the top. Each of the inputs has 2 bits represented as an integer, 0 up to 3 here. This truth table is a 4x4 table. So in general, if you have an n-bit input function, then you're going to get a 2 to the n by 2 to the n bit table, which is where this inherent kind of expense comes in. Okay, but say we have a reasonably small table for now, then let's describe how this preprocessing works. So the trusted dealer will generate two random shifts called R and S, and use these to permute the rows and columns of the table. So the shift R will first be used to permute the rows. So in this case, if R equals 3, then you take every row and just cyclically shift it 3 rows downwards. And then we repeat the same thing for the columns. So if we pick a shift of 1, then after we shifted the rows, we just shift the columns cyclically 1 column at a time. Okay, so this is a kind of scrambled or permuted version of the table we now have. And then the trusted dealer is going to secret share this truth table. So when I talk about secret sharing today, I'm not doing Shamir secret sharing or anything like that. It's very simple kind of additive secret sharing, which most of you have probably seen before. In this case, it's just two parties and it's XORing secret shares that XOR together to get the result. So you first sample one share at random, which is just a random matrix, the same size as the table. And then you generate the second share, this matrix MB, by XORing the first one with the values that are stored in the table. So that you take MA and MB and XOR them together to get the permuted table. Okay, so that's what our trusted dealer does. So it samples these random shifts, R and S, and secret shares, distributes R and one share MA to Alice, and then S and the other share MB to Bob. Okay, now they want to evaluate this function f. So they have some inputs, x and y. So all they will do is Alice will first send x plus r modulo 2 to the n. So representing the bit string of the input as an integer up to 2 to the n minus 1. And then Bob will do the same for his input, compute y plus s mod 2 to the n, and send this over. And then Bob will additionally take entry uv from this the secret share of the permuted table and send this across to Alice. So now Alice can take the same entry corresponding to her share of the table, so this is MA of uv, then XOR this with Bob's share, and then precisely because of the way the preprocessing was generated, this will give you the result of the function f. So when you XOR this together, you get the permuted table at index uv. U is x plus r and y plus s, so you've just applied the same shift as the dealer applied originally on the actual data. And then, okay, so what about the security of this protocol? So let's look at what's being sent over the network. Well, first Alice and Bob are simply exchanging their inputs masked with these random masks R and S. So since this is a one-time protocol, we only use these masks from the preprocessing once, then this is just a one-time pad of the inputs, so it's perfectly hiding. And then the only other thing you might need to worry about is this MB of UV value, which Bob additionally sends across to allow Alice to compute the output. But if you look at this, then the only place this is being used is to compute the output here. So if Alice somehow knew the output of the function already, then she would already actually know the value which Bob was going to be sent, just because of the one-time pad of the secret shares. So kind of more formally, if you think about it, how you improve security, then you could actually simulate this message given only the output and Alice's view of the protocol. So this is a perfectly secure protocol, and it's very simple. The communication complexity is essentially just proportional to the size of the inputs. So that's pretty much as good as you can get for MPC. You have to send something to represent your inputs. So that's optimal. And then the downside, of course, is the exponential storage overhead of these shares of the truth table and the dealer who has to generate this. Mm-hmm. Mm-hmm. Yes, yes, of course. Yeah, that's true. Yeah, so even though you have this exponential storage overhead, if the size of the table is not too big, then in some cases this can actually be quite a practical protocol. And especially, it's also been used for as kind of building blocks, or similar techniques have been used as building blocks in larger protocols where you might try to decompose a circuit or a complicated function into several sub-pieces which might be easily expressed as lookup tables that you can evaluate individually using something like this protocol. And this is a method in the tiny table protocol just from a few years ago. Okay, so that's the kind of simple warm-up. Now for something a bit more expressive, or at least less expressive and efficient, is a method of doing MPC for arithmetic circuits. So the passively secure version of the classic GMW protocol, modified to fit this preprocessing model which we're using. So here we're going to be computing arithmetic circuits. So this is still not really a kind of ideal description of a function. So if you have some piece of code and want to convert it to a circuit, it's a bit of a pain, but it's way better than converting it to a truth table. And it's also a useful kind of building block towards creating useful representations of programs you might want to compute. So in a circuit, we have a bunch of wires connected to gates. Have these input wires at the top here, which go through the gates, which are additions and multiplications over some finite field. So this could just be integers modulo p. And then at the bottom, we have the output layer where every wire is some output of the computation. Okay, so in this GMW protocol, we're going to proceed through the circuit in a gate-by-gate manner, such that at any point in the computation, we'll maintain this invariant, such that for every wire, which stores some value x along the wire, then this x can be represented by this set of n field elements, x1 up to xn, which represent an additive secret sharing of the secret value on the wire x. So each party holds some value xi, such that when you sum these up, you get x. Okay, and also when you look at kind of n minus 1 of these secret shares individually, we want them to hide the secret. So these shares should be uniformly random, at least when you look at them alone. Okay, so that's the kind of the main property we need for the duration of the protocol. Did I turn this off? Or maybe the battery died? Ah, no, it's back. It's okay. Okay, so that's the kind of secret sharing invariant that we have throughout this protocol. Now let's look at some of the operations we do. So first off, at the start of the circuit, we have the input wires, where each wire will be associated with some input from one of the parties. Say we have x held by party pi. Then pi just needs to distribute this set of random secret shares to all the other parties. So for every party pj who isn't pi, you'll just sample a random xj and send this random value to pj. And then you compute your own share xi by taking x minus the sum of all the other shares you generate, which creates this simple random additive secret sharing. And clearly this stage doesn't leak anything about the input, just because every share is random. Okay, now jumping ahead to the output wires of the circuit, at some point we have to open some values. So to open a secret share representation, of course, everyone just sends their share to everybody else, and then you can reconstruct x by summing up the shares. Maybe one thing to remark here is that if you do this naively, then this will actually give you some quadratic communication costs with everyone sending n-1 field elements. But you can also easily optimize this by, say, sending all of the shares to one party who reconstructs the result and then sends this back to everyone else. Remember, this is just passive security, so we don't care about someone adding some error when we don't expect it. Okay, so now let's get to the basic operations of the gates in the circuit. Okay, so first consider linear gates, so additions of two field elements, or maybe multiplications by a constant. So here I'm combining those two gates into one and just considering a linear operation of two secret shared values, x and y. So since additive secret sharing is linear, you can just take your shares, so pi has xi and yi, and apply the same combination, so multiply xi by a public constant a, and add this to yi times the public constant b, which represent the linear function I'm computing, and then take these to compute my share of the output y. Okay, so then when you sum the shares of zi together, you just get a times the sum of the xi's plus b times the sum of the yi's, which gives you ax plus b times y. Okay, so linear operations, all good. If we want to add a constant, we could also do that. Have to do it slightly differently here. So suppose we have some public constant c, which you want to add to a secret shared value x. And then this time you just need one party to add c to their share, and then everyone else keeps their share the same. So P1 computes x1 plus c, and everyone else keeps xi to get x plus c. Okay, so this is all very nice, and we don't have to communicate at all for these simple gates. But what we haven't done yet, of course, is multiplication gates between two secret shared values. And this is usually where things start to get a little more interesting, a little more challenging in MPC. And also at this point where we have to start using the trusted dealer, which we haven't even looked at yet. Okay, so suppose we want shares of the product of two input wires x and y. Now what I'm going to do here is write x times y in a slightly different way, just by kind of adding 0. So x plus 0 is x plus a minus a for some value a. Y plus 0 is y plus b minus b. So x times y, you can write like this. And then I'm going to multiply out this, this product by looking at x plus a and y plus b and kind of treating them as a single term. So we get the four expanded terms, x plus a times y plus b, and then the cross terms here, and then the final product, a times b at the end for a times b. So at this point, it doesn't matter what a and b are. Let's just see if we can get something useful out of this. So now, if you highlight things in the right way here, and think of the red values as being secret shared, and the blue values as being public values, you can see that x times y is now a linear combination of the red values on this row here. So that means if we have a and b, and a times b, all secret shared, and we somehow, in the clear, have obtained x plus a and y plus b, then we can compute the products as this linear operation here, which we know we can do locally from all the previous operations. So how do we do this? Well, if we have shares of a and b, then we can do one kind of opening operation to compute x plus a and y plus b. And then we need to rely on the preprocessing to get these kind of shared values a, b, and a times b. Where for security of the open values here, of course, now it's clear that we need a and b to be uniformly random in the field. So what this is doing is reducing the multiplication of the two kind of input values x and y to multiplication of two random values, which we know we can do in the preprocessing phase. So we still have to do a multiplication, it's just preprocessing it instead. So we have to do these two openings in the online phase. So then the full multiplication protocol, first we take this multiplication triple, or Beaver triple, coming from the technique from Beaver, who first invented this kind of preprocessing. And then we open x plus a and y plus b by broadcasting the shares, and then compute this linear operation the same way as before. Okay, so that's multiplication gates. That's the only thing you have to interact for, apart from the input and output gates, when you do the GMW protocol. So with passive security, this gives you a very nice simple protocol where the main communication, at least for large circuits, are these two openings for every multiplication. So that can be around sending 2n field elements over the network. Okay, but what about active security? Can we get something as good as that in the active secure case? Well, it turns out you can, at least. When the field size is large enough, we can get almost essentially the same complexity, maybe with some kind of extra factor 2 computational overhead, but with fairly lightweight methods using information theoretic max. Okay, so before talking about how to do this, maybe just think about the problem with an active adversary in the passive protocol. So the main area where, or the only area where something can go wrong is, of course, when you're sending something over the network, which is mostly when you're opening something. So during the multiplications or during the output wires. And since we just have additive secret sharing, because we don't have any way of kind of detecting whether someone is saying the right share or not, so a corrupt party can always add an error to their share xi and it just leads to the same error, ending up on the output wire of that gate or the output of the circuit and breaks correctness. An interesting exercise to think about is also whether you can break privacy in the same way. In this case, it turns out a little more tricky and maybe depends on the kind of function you're evaluating, but it's nice to think about, and I won't go into now. Okay, so we just need to essentially protect against these kind of attacks when we open secret shared values, and for this we'll modify the type of secret sharing we use by adding these information theoretic max. And I'm going to talk about these two approaches, which are firstly macking the shares, where you essentially add a mag to every share in the underlying additive secret sharing scheme. Well, the second approach, which is more efficient but a little more complicated, is sharing the max, and essentially involves creating a single mac on the underlying secret that's being computed upon, and then creating shares of that. Now, this is what's used in the speeds protocol, whereas the previous mac the shares approach is used in the Bedoza and TinyOT protocols, which are for multi-party computation over large finite fields or for binary circuits for the TinyOT case. Okay, so this first approach where we mac the shares, we use a kind of classic information theoretic mac on a secret x, where you compute alpha times x plus beta in a finite field, where these alpha and beta are random keys for the max scheme. So the way we use it here, the alpha will always be fixed. So for every mac we compute, it'll have the same alpha, but we always sample a random beta for every mac you compute. This is kind of easy to see if you look at the fact that we want a hiding property of the max. If beta is fresh, then that perfectly hides x, otherwise you'll probably run into some problems. Whereas the alpha is only used to prevent the forgery of the max scheme, and it turns out this can stay the same. Okay, so the main property of this is that given some value x and a mac of x, if I don't know the key, then coming up with a mac on some different value x prime essentially requires guessing this key alpha. So I'll quickly move to the board and write this out now so you can see why that is. So let's suppose we have an adversary who's given x, and additionally say m, where m is alpha times x plus beta for some random mac keys alpha and beta. And then the challenge of this adversary is to come up with some x prime and a mac m prime, which passes the check with the same key. So m prime is equal to alpha times x prime plus beta. Okay, now if they manage to do this, then we can look at the difference. So m prime minus m. So we have the same beta in both cases and alpha. So the betas cancel out, and you just get alpha times x prime minus x. Now, of course, if they forged a mac, then we assume that x prime is different to x, which means this is non-zero, so we can divide by x prime minus x and get alpha is equal to m prime minus m times by the inverse of x prime minus x. So this last line here requires that we're working in a finite field, so modulo p if we're doing modular arithmetic. And then we've shown that anyone who can win this game has guessed the MAC key alpha, so as long as we're in a large enough finite field, then this will only occur with some tiny probabilities, 1 over the field size. Okay, and you might be wondering, okay, what happens if we're not working in a large field? What if we want to do something over, say, binary circuits? Well, there's an easy solution, which is essentially just to repeat this several times until you get kind of negligible probability. So you can use several 1-bit MACs and concatenate them until you get a 64-bit MAC, which you just treat as a vector of field elements over the base field. Okay, so finally, the other important property of this scheme, which is the main reason we're using this information theoretic MAC scheme here instead of some standard MAC like HMAC or something, is that this is a linear MAC scheme. So if we're given, say, MACs on 2 values, x and y, so mx and my, let's say mx is like this, and then my is going to be, so remember we have the same alpha even for different MACs, but this time we have a different beta, so we have, say, beta prime instead of beta. And now we can compute a MAC on x plus y by simply adding together the 2 MACs on x and y. So this gives us something again with the same alpha, but here we get a different beta, which is just the sum of the 2 betas, beta plus beta prime. So the main thing to note here is that if you compute the sum of the MACs here and then want to verify it later, then the verifier who holds the MAC keys will also have to kind of sum up the betas on the appropriate keys there and do the same operation. But thanks to this linear property, that means all of the linear operations we did before, like the addition, multiplication by constant, and addition of constant, essentially carry exactly the same when you have MACs on all of the shares, as well as the additive shares. Okay, so then the main strategy for converting the previous protocol to have active security is to modify the secret sharing representation. So for every share xi, we add a MAC to xi under a key held by pj for every other party pj. So that means for each share xi, you'll essentially be adding n-1 sets of MACs, which pi will have to keep hold of and then use during the computation. And then pj will get a key for each for that share, and we'll have to store this. So it's the same alpha j value for everyone, but a different beta. And then we, of course, also need to modify the preprocessing phase. So instead of just random additively shared multiplication triples, we have to add MACs on the triples. And additionally, so that we can actually create these MACs on the input wires of the circuit, we need to work a little harder there because, again, I can't just create a MAC without knowing the MAC key, which someone else has to hold. So here you can create a separate kind of random preprocessed sharing, which is just a set of random additively shared values with MACs on, and then use those to authenticate inputs by kind of one-time pad encrypting and doing linear operations. I won't go into the details, but that's quite straightforward. Then finally, of course, whenever we open something during multiplication or at the end of the circuit evaluation, as well as sending the shares, you have to send the MAC shares so that each PJ can check their MAC on XI. Of course, this means we can't rely on this optimized opening, which I mentioned earlier. So actually, every time we do an opening, now you have n² communication instead of m. So this kind of quadratic blowup is now the main problem with this MAC scheme. So because we've got essentially n² MAC channels going on for every secret shared value x, then this gets blows up pretty quickly as the number of parties increases, and the communication costs and the storage costs from the preprocessing blow up proportionally. So there is one solution which I've realized is actually not right. I think this doesn't apply to this protocol. So I don't think we can reduce the communication down to better than O(n²). You can postpone the MAC check at every multiplication gate until the end of the computation, but you still have to send the shares, so just ignore that. But there is a solution. And then, sorry, so the solution for reducing the storage, which also solves the communication problem, is to switch to the different kind of max which are coming up. So the solution is just to do something different, basically. Okay, so previously we mapped the shares. Now we're going to share the max. So this time, instead of looking at the shares, we'll look at the secret underlying value x on a wire, which in general nobody knows, but let's try to add a mac to it anyway. So here we use a slightly different scheme where instead of doing alpha times x plus beta, we just compute alpha times by x. Now it might seem that, okay, this is no longer going to be hiding. You know, if x is 0, then I can see that that's the case just by looking at the map. But of course we're not giving out the mac here, we're secret sharing it, so this isn't a problem. So for every value x here now, instead of having pairs of max on the shares, then we just augment this set of shares with a single set of shares m1 to mn. Each party pi gets mi, such that the m's sum up to this mac alpha times x, where x is the sum of the xi shares as before. So that's very simple. But now the challenge is, no one actually knows these macs. No one knows this mac key alpha, which is also additively secret shared. So how do we even check these macs without revealing the mac key and without revealing the max, which would also break privacy? Okay, so suppose we've opened some value x prime just by sending the shares, maybe naively, insecurely, which could have some error e on it, and then we want to check the mac. So each party can define this value di here, which is the share of the mac key alpha I multiplied by the open value x prime minus the max share mi. So notice that if you sum these up together, then you just get the mac key, the sums of alpha multiplied by x prime minus the sum of mi, which is just the mac on x. So if x prime is equal to x, then this will clearly get us 0. So they just commit to these shares, open the commitments, and check these sum to 0. So why does this work? Well, suppose we have this error e in here, and when you sum up these values d1 up to dn, you end up with e being multiplied by the mac key alpha. Now, as well as lying during the opening, an adversary could also send some incorrect, say, shares in this d1 to dn, maybe up to n-1 of them if they've corrupted n-1 parties. But all this is doing is just introducing some additive error in this computation, which has to cancel out with this alpha times e, which is always going to be there. So then just for the same reason as the pairwise max before, since we can invert in the finite field, then coming up with something to cancel out alpha times e requires guessing alpha. So again, we get 1 over the field size, forging probability. Okay, so let's just compare these two schemes briefly. So we can look at a few different metrics here. We can have storage costs, computation, communication, round complexity. So on the left we have the pairwise max, or macking the shares. On the right, the global secret shared max. We share the max. So all of these costs are quadratic on the left when we look at the storage from the preprocessing, the computational complexity, and the communication complexity for a single multiplication gate. Whereas when you switch to the shared max, all of these go down to linear when you count the total cost of the number of parties. And for the communication, note that this is because when we're opening something, we can then rely on this optimized opening where you just send the share to one person who sums it up and sends back the results, because the only thing you're checking the mac on is the results. It doesn't matter what the intermediate shares were in the first place. When you have to actually do the mac check, things get a little more different, because now instead of just sending the macs and checking them locally, we have to do this interactive mac check protocol where we commit to something and open it and then check this. So this is 3 rounds if you count sending the shares of the value opening as well, compared with one round previously, since everything can be opened and checked in parallel. But if you use this extra technique, which I haven't described, where you can delay the verification of all of the MACs until just before the end of the circuit computation. So it could be that when you're doing some multiplications, that you might have some incorrect results. So you're just sending shares without checking MACs. But since you're not revealing anything until the end of the computation, it doesn't matter if whatever you've computed is garbage in the meantime, as long as you check the MACs before opening the final result. And you can do these kind of in this batch verification method very efficiently, then it will work out okay. So once you do this, then as long as you have a kind of reasonably large function with enough multiplication gates, then the extra couple of rounds for this mag check won't really matter anymore, and the sharing max approach will pay off. But remember, this is only if you care about the scalability with a number of parties. If you only want to do two-party computation, maybe three-party computation, then the simpler approach may well be the better one. Okay, so that's the end of the topics I wanted to cover. So we've covered passive secure protocols with the one-time truth table and the GMW protocol, and then showed how you can make that active secure, which gives you the Bedeaus and the Speeds protocols, or at least the online phase of those. So if you want to read a bit more, there are some resources here. I'm not going to go through them now, but you can look at them when the slides are online later, and look at the papers or tutorials, which might be helpful. And I'll be happy to take questions. Yeah.
Can we use the speeds protocol for reactive functionalities? Because the privacy of the MAC key, I guess, will be revealed if you postpone everything towards the end of the computation. But then you can't reuse the same alpha for the future batch of inputs.
So you can use it for reactive functionality still, because when you do the MAC check the way I described it, which is actually in the second speeds paper and not the first one, then you're still never revealing the MAC or the MAC key. So even though you postpone it until you output something, after you've checked, you can still continue to use the MACs again as many times as you like.
Any other question? Yeah, I think. Small participation by you.
Thank you very much.